Swayam Prabha. Digital India. Educated India.
We were talking about the open system. So, and accordingly, we had modified the four fundamental equations of thermodynamics, which we had derived previously when we were talking about a closed system. Then we talked about in the last class about the open system when we had the mass transfer possible between the system and surrounding, and we modified the four fundamental equations for the open system. So according to the fundamental equations of a closed system, we had the change in total internal energy or enthalpy or the Gibbs-Helmholtz energy or the Gibbs free energy by certain set of terms which are shown in the screen. Now, what we had said, as you can understand, when we are talking about, say, let us talk about G. When we are talking about G, we had the criteria of constant temperature and pressure. And under that condition, when we were defining this, we are saying that how G is changing with temperature is a measure of the entropy of the system. So we had written this as S, and that was a minus sign. Similarly, we had said how the G is changing with pressure is a measure of the volume. So we had modified that and replaced that as volume and dP. So the equation which we have here is actually coming from the fundamental equations on variation of the fundamental variables of each of the terms. As you remember, this was the one which we had taken G for a, say, any system. When we had G, we had this equation as the fundamental equation, and how we had derived that, we had differentiated the G with respect to the fundamental variables, and for G we say it is temperature and pressure. So how G is changing with temperature is what we had seen with total change in temperature, how G is changing with pressure with total change in pressure, plus now we had added some certain new terms, but here, as we know, this we defined as minus S from the Maxwell's relation, and this we defined as V from the Maxwell's relation. So this is the two definitions we had. So accordingly, we had the equation of G being minus S delta T plus V delta P. So it is actually derived from the fundamental variables and how the G is changing with the fundamental variables. And from Maxwell's relation, the first variation of G with temperature we had taken to be minus S, and the first variation of G with P we had taken as volume. Now, how G is changing with the system parameters is the thing which we are looking into. If we are having an open system, then there's exchange of matter. So there will be a change in number of moles as well. So if we have two components in a system, suppose water and ethanol. So how the G is changing with ethanol, the moles of ethanol, keeping all of the rest as constant, like temperature, pressure, and moles of water as constant, and total change in the moles of ethanol. This is what is represented. Then I will say this change in G with the moles of ethanol is the partial chemical potential of ethanol in the system. Similarly, how G is changing with water. Now I keep the temperature pressure constant as usual and see how the and also the number of moles of water as constant, and the total change of sorry, here I'm talking about one is ethanol. So ethanol moles is constant. Now total moles of water. So now I say the change in G with the moles of water is the measure of the chemical potential of water. So this equation gets modified as minus S delta T plus VdP, which is coming from the closed system part. Now these two additional terms is one is chemical potential 1 into the change of moles of 1, that is chemical potential of ethanol with change in moles of ethanol plus change the chemical potential of water with change in moles of water. If the ethanol water is the system I'm taking. So then if I have an n number of such components, then I can say that I will sum it over all the components, chemical potential of each of the component multiplied by the change of that moles of that component taken all over the system, keeping changing one at a time. When I'm changing with number of moles of water, the ethanol remains constant. When I'm changing the number of moles with ethanol, then water remains constant. This is what we had taken. So if you remember, this is what we had modified, and I had said that the chemical potential which can be written as whatever system variables we are taking and whatever the constants are. Suppose if I'm talking about internal energy, then S and V are the constant variables. And if I'm taking the number of moles, then N, whatever moles are there, if there are no more than one component present, then I should not be equal to J when I sum it over all the components. That means each time I'm keeping the moles of one constant and varying the other. So I said that the chemical potential of each of the thermodynamical potential parameters can be defined with respect to their number of moles of each of component present. Always remember that the constants will be the constants associated with that particular thermodynamic potential. For U, it is S and V. For H, it is S and P. For A, it is T and V. And for Gibbs free energy, it is T and P. And the additional term being the number of moles. So please remember what we are talking about here. So this is what we had said, and we had said that for a pure compound, the chemical potential is nothing but the molar Gibbs free energy, because we are talking about how the Gibbs free energy is changing with respect to moles. And if I talk with respect to moles, whenever I'm talking about, that is going to be the molar volume or molar Gibbs free energy. So molar values, if I multiply with the number of moles, will give me the Gibbs free energy. Okay, so this is the definition of chemical potential. And here what we have the temperature pressure constant, and we need not talk about other moles because it's a pure compound. Okay, so the chemical potential is slightly different here because we are talking about the molar energy and we are not having any component Ni equal to not equal to J component present here. That's the only difference you have when I talk about the molar Gibbs free energy. So what you have, we summarize the properties of it. So the thermodynamic relation applied to the closed system which we had, the G, U, enthalpy, these are all extensive property. They are depending on the mass. At equilibrium, what happens? The chemical potential of a species is same throughout the system. The chemical potential of each of the species, if I take a system, if I have a component present, the chemical potential of that component will be equal or same throughout the system when they have reached the equilibrium. Okay, and if there is a reaching our equilibrium, then there is no further spontaneous process that can take place because they have already reached the equilibrium. Until the equilibrium is reached, we have a process ongoing, and we are having an ongoing process until we reach the equilibrium. So if we have reached the equilibrium, then the chemical potential of the species in the system should be same everywhere. So how I have defined the chemical potential? Please look at the way I have defined. Chemical potential is defined with the variation of G with the number of moles, is the same as variation of H with number of moles. It's the same with internal energy with number of moles and Helmholtz energy with number of moles. Only thing you have to keep remembering is the things which you are keeping constant. When you are talking about G, it should be temperature and pressure, and obviously the number of moles being the whatever number being present. If I'm taking a number of components, then it should be I should not be equal to J. That means each of the species, when I'm having, I keep the variation only for respect to one species and the other species being same for the variation. So if I similarly for H I have SNP, U I have SNV, and A I have temperature and volume. So this is how we define the chemical potential of a species in a system. Now, we have just now said for a pure system, it is thus just the measure of the molar Gibbs energy as far as the G is concerned. Chemical potential of a substance is the molar Gibbs free energy for that particular species in the system. For suppose I have ideal gas, then ideal gas G equal to G naught plus nRT ln P by P naught. This we have seen how while we were deriving the expression for variation of G with pressure. So this is the expression we had got, and it's a standard equation which we are going to be using very often. So this is the variation of G. So if I want to write down in terms of the chemical potential, it is going to be divided by the number of moles for that particular gas. And if I'm talking about ideal gas, then it should be nothing but the chemical potential equal to chemical potential at standard plus RT, because the N is going to be gone and rest of it going to remain the same. For multi-component system, obviously this is going to be replaced by N is going to be replaced by Ni, so that we have to see the variation of the chemical potential of the ith species, keeping the other species constant. So the chemical potential of a species is constant and everywhere in the system, that we have already said. And it is a G is a extensive property, while the mu chemical potential or the molar Gibbs free energy is an intensive property. If that is so, that means we can write the total G is nothing but the moles of the species 1 into the chemical potential of 1 plus the number of moles of the second and the chemical potential of the second, so on and so forth. So we can write, in other words, the total number of moles of each species multiplied by the chemical potential summed over all the species is the total value of G. Or we can replace the chemical potential by the molar Gibbs free energy. Okay. So I hope you have understood what the chemical potential means. So if I take 1 mole of a substance, 1 mole of a substance, sorry, n moles of a substance, for that, how we can represent G is shown here. G is equal to G naught plus nRT ln P by P naught. P naught is the standard pressure defined as 1 bar. So sometimes we may not write P, but you remember it is always there in the denominator as 1 bar. So the chemical potential of a multi-component system can be the chemical potential at defined equal to the chemical potential at standard state plus RT ln P by P naught. So you understand what is the difference between the two equations. You have just defined the G differently. Here you have taken for one component, we had written mu as G by mu, and for multi-component we always write mu I. That means we have a variation of G with number of moles of the species present. Suppose, now let us talk about the conditions for transfer of matter from one region to the other. Suppose I have a system of one component, only one component, and in 2 phases, that means 2 parts. Okay, consider a small amount of this species I moving from phase A to phase B at a given temperature and pressure. Okay, so if a small amount of species of one component is present, and this one component species is getting transferred from the phase A to phase B, then what will be the change in the Gibbs free energy of A, and what will be the change in Gibbs free energy of B? Since the number of species which is getting transferred from A and B, this is giving up some amount of the number of moles. So there will be a decrease in number of moles of in this side. So I can write the chemical potential of the ith species equal to G of the species equal to chemical potential of I into the change in number of moles. What is the number of moles change? It is minus Ni. That is, small change means dNi. Very small amount of A species is ith species is getting transformed from section A to section B. Okay, and the change is represented as the number of moles of ith species at phase A is equal to the number of moles which is gained by the phase B. Okay, this is how we represent. Now, what will be the chemical potential of the species in the component in the section B? This is another phase. From here, the transfer is getting to this part. So this is gaining the amount of the number of moles which is being transferred from A. The species being the same. The same species now is going to be being transferred from A to base B. So the B part will have a gain in number of the species I. How much? By the same amount which is getting transferred from here. So it will gain plus dNi. Now, what is going to be the total change in G? Total change is G will be the change in G of A plus change in G of B. So I can write mu I A, that A means in this part component ith species in the part A, into minus dNi plus the chemical potential of the ith species in B into the change in number of moles of I, that is dNi. So I add these two up. If I add these two up, what do I get? I get the difference in chemical potential of the ith species in B minus the chemical potential of the ith species in A into dNi, because dNi is the amount which is getting transferred. Right? Now, I know for a process to be spontaneous, the G has to be negative. Right? So now I plug in the conditions for what will be the process, whether it is going to be spontaneous or not, by evaluating the value of G from the expression I got. Now, what will happen? When will this become negative? You see, if A is greater than B, then what happens? When A is greater than B, what happens? There is going to be a decrease in G, right? So I have a decrease in G less than equal to 0 when A, the concentration or the chemical potential of ith species is A in A is greater than the chemical potential of that species in. Now, what happens if it is B is greater than A? The chemical potential of the species in section B is in the part B is more than the A. What happens? Then this becomes positive. That means what do we get? What can we say? What can we say? That means it is not spontaneous. That means the transfer of the matter is not going to be spontaneous when the chemical potential of the ith species is big, more in the B section, right? And when it will be reaching equilibrium, when the chemical potential of the ith species in both the phases are going to be same. Okay, so equilibrium is reached when the chemical potential of the species is same, equal throughout the phase, throughout the system. So if the chemical potential becomes equal, then that is the place where the transfer will cease to occur. Whatever transfer of the number of species was being done will stop to occur when the chemical potential of the ith species in the two components, two phases become equal. Okay, so the transfer of G is from always higher to the lower value of chemical potential. So chemical potential is, as like any other potential, behaves from downhill process from higher value to a lower value. Okay, and when we say the chemical potential of the two of the species in two components or two phases are same, that means we are having at the system at equilibrium and the species are coexisting, right? Suppose we have the equilibrium can be represented. Suppose we have ice and water in equilibrium. How we represent that? The chemical potential of ice at a given temperature and pressure is equal to the chemical potential of water at the same temperature and pressure. So this is how the equilibrium is written when in two phases. When the species is same in the two phases, then we say the process is at equilibrium, right? Now what happens if you are having a mixture? Suppose the mixture behaves ideally at a given temperature and pressure. And suppose there is ith species and the mole fraction of that component, ith component will be represented by, let it be represented by xi. And what is going to be the partial pressure? Partial pressure of the ith species will be the mole fraction into the total pressure, right? Mole fraction into the total pressure. Now let us come to the equation of chemical potential. According to the equation of chemical potential, we have defined the chemical potential is something like this. Chemical potential equal to the standard chemical potential plus RT ln P by P naught. This is how we have defined it. So let us write down that. So chemical potential of the ith component is the chemical potential of the ith component equal to the chemical potential of ith component at standard state plus RT ln the pressure of the ith component divided by the P naught. And I say in a mixture, if there is a mixture, then the chemical potential of the ith species is nothing but the mole fraction into the total pressure, right? So I write down this in terms of the pressure in terms of the mole fraction into the total pressure. So I write down mole fraction into the total pressure. Now you separate them out. Now separate, make the take the log and separate them out. What you get? Chemical potential of the ith species at standard state plus RT ln P by P naught plus RT ln Xi. But while this is, we know, is the chemical potential of the pure state, right? This is how we have defined. So the chemical potential of the of the species at a given temperature and pressure is nothing but the chemical potential at the pure state. I mark this as star, which is equal to this particular whole expression mu I and raised to the standard state plus RT ln P by P naught. This is the total pressure. So this is nothing but, this red portion is nothing but the chemical potential of the pure species. And this is, as it is, RT ln Xi. Xi is the mole fraction, right? So what can we say from here? What will happen to the chemical potential of the species when they are in the pure state and when they are in the mixture? Anybody can say? You see, chemical potential of ith species in a mixture, this is the chemical potential of the ith species in mixture, is nothing but the chemical potential in the pure state plus RT ln Xi. Xi is the mole fraction, right? And Xi is a mole fraction will be always less than 1, right?
Yes, ma'am.
If it is less than 1, then it becomes minus. I put 2 pluses here. Sorry. So it is going to be minus. This term is going to become minus. So what we can say?
Yes, ma'am.
The chemical potential of the ith species in a mixture is going to be less than the chemical potential of that same species when it's in the pure state, right? So chemical potential of a species in a mixture is always going to be less than the chemical potential of that species when they are in its pure state. Okay, so let us consider an example. Let us consider an example of a cell, our biological cell is put in a salt water, and what will happen? When we have the chemical, when we look into the chemical potential of water, which is inside the cell, I say that is pure water, and in the outside is the salt water, then what will happen? The chemical potential is a downhill thing. The water chemical potential of water inside the cell is going to be more than the chemical potential in the mixture, which is in salt water. So what will happen? The water will start flowing from the cell to the outside. It's a downhill process. Higher potential to the lower potential, the flow is going to be spontaneous, right? So what happens? The water from the cell will start draining off and going towards the outside in the salt water. So what will happen? The cell will die, right? So the chemical potential is always a downhill process. A species is going to always move from a potential which is higher to a potential which is lower. Chemical potential and its downhill drive to equilibrium is the guiding principle for all phase transition, chemical reactions, and biochemical processes. Okay. Now we talk about another term. When we talk about an open system, we are talking about chemical potential. It is the species which is existing in a mixture. Now, how is that different from a partial molar quantity? Partial molar quantity, if you see, is defined as J. We are talking about an open system. We are talking about a mixture. Okay, so any component, any thermodynamic potential or any thermodynamic variable, the partial molar quantity of that whatever variable we have, it may be the U, H, S, A, G, and V. Volume, Gibbs free energy, Helmholtz free energy, entropy, H, enthalpy, and internal energy. If these are the parameters which we are thermodynamic parameters we are looking into, then how do we define the partial molar quantity of each of these quantities? What we define is obviously partial molar means per mole. So I define the partial molar quantity of any substance as that particular property, change of that particular property with the number of moles of the species. Okay, but here I have defined at constant temperature and pressure. Again, the partial molar quantity of a component, I suppose it's a species I, the thermodynamic potential of that, whatever thermodynamic potential you're measuring, change of that thermodynamic number of moles of that species, keeping other species constant, if there are a number of species present. So again, partial molar quantity is going to be an intensive property, while the thermodynamic parameter which we are saying will be extensive. So extensive property will be nothing but the summation of the number of components of each of the species present into the partial molar quantity summed over all the species which is present. Where again, I have to mention that I is not equal to J, because if there are a number of component present, I, K, J, L, M, and whatever, means one component species change will not be, will have to have the other species constant. Okay. Now have a look at this. It is an intensive property, partial molar quantity we have said. Now have a look at what is the difference between chemical potential and partial molar quantity. You see, we have defined chemical potential just now. We had taken per mole of each of the species which we are talking about. How is it different than the chemical potential? The difference lies in the definition. Definition is the thermodynamic parameter which we are seeing. We are seeing the change of that thermodynamic parameter with respect to the number of moles of each of the species present, taking one at each time, always keeping temperature and pressure constant. But when we take when we talk about the chemical potential, then we do not keep the temperature pressure constant. Am I understood here? Suppose I talk about U. If I want to find out the partial molar quantity of U, then how should I write? How U is changing with the number of moles I of species I, keeping temperature pressure constant, and conditions is that I is not equal to J. Had it been chemical potential, then what would that become? What is U variable, fundamental variables of U? Entropy and volume, right? So instead of temperature and pressure, this would have been entropy and volume. See, chemical potential is defined from the fundamental equations depending on the total, whatever the fundamental variables for each of the thermodynamic parameter which we see. Only in the Gibbs free energy do we have temperature and pressure. Others will be, for Helmholtz it will be temperature and volume. For enthalpy it will be entropy and pressure. For internal energy it will be S and V. Am I understood? But when we talk about partial molar quantity, it is always defined at constant temperature and pressure. Am I clear? It is always defined at constant temperature and pressure, with the number of moles, rest of the number of moles being constant. So that means you can understand, for a Gibbs free energy, the partial molar quantity is equal to the chemical potential. Am I clear now? Anybody? There is confusion?
Yes, no, ma'am. It's clear.
So only when we write the partial molar quantity of G, only G, since it is defined at constant temperature and pressure, so only for G, the partial molar quantity becomes equal to the chemical potential. But when we talk about A, the Helmholtz free energy, and if I define at temperature and pressure, this is not going to be giving you the chemical potential. This will only give me the partial molar quantity of Helmholtz energy. If I have Helmholtz energy changing with number of moles of any species I at given temperature and volume, then it would have been chemical potential. But when I define it in terms of pressure and temperature being constant, it will always be the partial molar Helmholtz free energy of the species I. Okay, please do not confuse this. So similarly, you can understand that we can write down how the change in each of the thermodynamic parameters which we are looking into is being a intensive property. The sum of each will be given multiplied with the number of moles will give you the measure of the total enthalpy or internal energy, whatever parameter we are talking about, if they are defined at temperature, at constant temperature and pressure. Okay, because here we have defined the partial molar quantity into the number of moles of that species, and where partial molar quantity is defined of the variation of the thermodynamic parameter with the number of that number of moles of that species at a given temperature and pressure. Only thing is, both are change per mole, but you have to remember that it is chemical potential is defined by the thermodynamic fundamental variables of the thermodynamic potential, while partial molar quantity is always with temperature and pressure. Now, chemical potential in a mixture, this we have just now talked about. The chemical potential of a mixture is equal to the chemical potential of the pure plus the RT ln the mole fraction of A. That means chemical potential of a pure state of any species is going to be greater than the chemical potential of that species in a mixture. Now, we have taken a number of things in terms of the thermodynamic variables. We have not talked about volume so far. When we talk about partial molar quantities, one of the very important properties which we monitor is the partial molar volume. How to describe physical property of a mixture? We are talking about a simple mixture. Knowing the properties of a pure ingredient, we have to have the idea of the knowledge of the properties of the pure ingredient. Suppose phase a simple mixture. Let us talk about only the volume of a mixture. If it's a perfect mixture, that means if I'm talking about gases, all the gases are ideal gases. If you mix them, then what happens? We assume there is no interaction between the molecules which are existing. The same can be applied to the internal energy, enthalpy, CP, whatever thermodynamic parameter we are talking about. Volume is one of the examples we are going to take up, because we are going to focus on partial molar volume, because we have talked about other thermodynamic parameters, but particularly potentials, U, H, A and G, but we have not talked about volume so far. So we are, for a simple mixture, what we are going to be looking into is the partial molar volume. And the example we have taken in the partial molar, in a simple mixture, is the volume of a mixture which is perfect or ideal. Then what happens? The total volume is nothing but the summation of the total number of moles of one species into the volume of the pure substance, in plus the total number of moles of that species plus into the volume of that fraction. And if I sum it over the number of moles of the ith species and multiplied with the respective volumes of the pure system, will give me the total volume. You know, volume is an extensive property. So if you add the all volumes of all the moles of the systems present, it should give you the total volume of the system. But what happens when you have a real mixture? When you have a simple but real mixture, what happens? We have intermolecular forces, and this intermolecular forces will give you a different volume. Let us imagine, this example is given in Atkins. Let us imagine a huge volume of water. Huge volume of water. And now I add 1 mole of water in addition. Just 1 mole of water in addition. Now if I measure the total volume of water should increase by, say, 18 cc, because 18 cc per mole is the molar volume of water, right? The total volume of the system will be addition of the total number of moles of that pure water which you've added, that is 1 mole, and that is 18 cc should be the increase. So the total volume should increase by 18 cc, because I'm imagining there is no interaction. Now what happens? Now let us add 1 mole of water to a huge volume of pure ethanol. I have a ethanol in large amount. Into that I add 1 mole of water. What should I expect? I should have an increase by the 1 mole of water is going to be 18 cc per mole. So the total increase should be 18 cc per mole. But what we see, the volume increases only by 14 cc per mole, which is the partial volume of water in pure ethanol. The reason for the different increase is that the volume occupied by a given number of water molecules depend on the identity of molecules that surround them. So when I define 1 mole of water in ethanol, I'm talking about the partial molar volume of water in pure ethanol. So the volume increase which we are talking about, the molar volume, the volume increase of the system is going to be different for different systems. I add water, 1 mole of water to ethanol, and I add 1 mole of water to benzene, may not be the same. Or if I say 1 mole of water to, say, acetic acid, with the volume change may not be the same. So this increase which we are saying is the partial molar volume of water in pure ethanol. So I have to define the environment in which I am putting the excess amount of water. That means whatever molecules is surrounding that 1 molecule or mole of water is having some say in the total volume. So this is what happens in a real system. Partial molar volume of a substance in a mixture is the change in volume per mole of the added to a large volume of mixture. Suppose I have, if you look at this is the partial molar volume, y-axis, and here I have the mole fraction. Okay. Here the example is of ethanol. You just have a look at it. Partial molar water, volumes of water and ethanol at 25 degrees centigrade. Just have a look. The partial molar volume of water, this is for ethanol and this is for water. That means the partial molar value of any component in a mixture is going to depend on the composition, because each molecule is going to have a different environment. Am I clear?
Yes, ma'am.
Okay. So just have a look at this. You have a partial molar volume of ethanol. Have look at the scale, and partial molar volumes of water. Is this side is representing that? And here is the mole fraction of water. That means with change in composition with the mole fraction of ethanol, I have a different value of molar volume of water. You can see how it's decreasing, coming to 1. And here how it's increasing. Okay. So, okay. So the partial molar volume of a substance is nothing but the variation of the V of a partial molar volume of a substance is nothing but the variation of V with the amount of V in the composition. So it is nothing but the slope of the volume versus the amount of that particular species present. Now have a look at this. This is having a value, this is the slope here, this is a value positive, while here you have a negative value, right? So the partial molar quantity, particularly when we talk about volume, the partial molar volume can have a negative value. Volume cannot have a negative value. Volume will be always positive. But the partial molar volume may have a negative value depending on how the volume is changing with the amount of A in a particular of that particular species in the mixture, right? The partial molar substance is the slope of the variation of the total volume with composition. As you see, the slope is changing with composition, various composition. Here you have one composition, here you have another composition. At B, at the composition where we have marked as B, then you have a molar value, molar volume value as negative. That means the overall volume of the sample decreases as A is added. Clear? So how the total.
This is something related to azeotropic mixture, which we learn in the solution chapter.
We apply this to that.
Okay.
Application of that is that you understand how the molar volume changes. So when we try to explain the isotopic mixture, we have this knowledge beforehand, right?
Yes, ma'am. Okay.
It's application of how you understand the partial molar quantities. The partial molar quantities is going to be depending on the composition of the system into which you are adding, and if a particular overall sample may the total volume may not be increasing, it may decrease if the slope of the partial molar quantity of that particular species in the composition is decreasing with the number of moles of that particular species in that composition. Okay.
Yes, ma'am.
So how the total volume changes when we change the amount of the amount of one of the components is how you define the uh, partial molar quantity. How the molar volume is changing with the a particular species, whatever we are for who which whatever volume we are trying to measure. Suppose we are talking about water in an ethanol mixture. What amount of water is the partial molar volume of water in the mixture is going to be the total change in volume with the number of moles of water, keeping the number of moles of ethanol fixed at given temperature and pressure. So partial molar quantity volume is going to be dependent on the composition. If I have a binary mixture, then the total change in volume is nothing but the change in volume with respect to one of the one of the component volumes of moles of one of the components, keeping the pressure temperature constant and the moles of the other constant, and the change of that number of moles of A. Similarly, plus the change of volume with the species, keeping the initial moles of the other one which is not changing is fixed, and total change in the number of species B, moles of the number of species B. So if you see this if I say is the molar volume, and this is a molar volume of the species in B. So whatever I have, the more change in total number of change in the total number of moles of A into the molar volume of A plus the change in number of moles of B into the molar volume of B into the change of moles of B. Okay. So we have always, if to find out this, this is actually, we have to read it this way. Okay. This is the expression we have. So the integrating with constant temperature and pressure conditions, the total volume will be nothing but the change in the volume A into the number of moles of A plus the total volume of B, molar volume of B into the number of moles of B. Okay. I hope we have understood that molar volume is going to be composition dependent. You can have a negative value of partial molar volume. And if the overall volume is negative, that means the total volume is going to decrease at that particular composition for that particular species being added. Am I clear? Am I clear?
Yes, ma'am.
Okay. Now, a follow-up of the partial molar quantity is the Gibbs-dewham equation. Gibbs-dewham equation states that if you sum over the number of species into the chemical potential, change in chemical potential of that species for all the species present in the system should add up to 0. This is to say, if I have a binary mixture, then the change in chemical potential or the for a particular mixture, chemical potential of one of the mixture cannot be changed independently of the other. That is what the conclusion is. One cannot change independently without the other being affected. If I'm talking about a binary mixture, so the chemical potential, if one is changing, the other is going to depend on how much the other component, chemical potential of the other components is changing. Now, how do we derive this? We derive this from the expressions of whatever all we know till date. We know the definition of G being extensive property is nothing but the chemical potential into the number of moles of that particular species summed over all the species present in the system. Okay, this is what the definition of G is. Now, suppose from the definition for a given system, two species A and B are there. So, what we have? The chemical, we have only two species present. So, from here, what can we write? Chemical potential of species A into the number of moles of A into the chemical potential of A plus the number of moles of B into the chemical potential of B. This is for G only. See, we are taking up only G. We are not taking about other things, because only for G, the chemical potential and the partial molar quantities are going to be the same. Okay. So this we have. According to the change in Gibbs free energy, if there is a small change in the composition of each of the species, how do we write? We write down the total change in G with respect to the variation of each of the components. That is how we have defined the total differential. If this is the definition of G, then dG, the change in D, when there's a small change in composition, can be given by the dG into number of moles of A, change in number of moles of chemical potential of A, plus number of moles of B, the change in number of chemical potential of B, plus now we change the number of moles, keep the chemical potential constant, and how the chemical potential of A into the change in number of moles of A plus chemical potential of B into chemical change in number of moles of B. This is how we get this. This is the equation we have defined for G. So we find out what is dG, the total differential. Each of the species have to be differentiated. And that is what we have done. Right? But from the fundamental equation of G at constant temperature pressure, what do we have? This is the fundamental equation at constant temperature and pressure. Chemical potential of the IH species into the number of moles of IH species is equal to delta G. Right? So if I want to write down in terms of the fundamental equation at given temperature and pressure, what do I write? I write chemical potential of A into the change in number of moles of A plus chemical potential of B into the change in number of moles of B. This is what we define. Now both are delta G values. So I equate the two delta Gs. Right? If I equate the two delta Gs, what is going to be happening? You see, this will go and cancel. This will go and cancel which one? Mu will be there. dA will be there. This one. And this will cancel this one. Right? I equate the two because both are dG values. Now, if I do that, then what I get only I am remaining with is the number of moles of A into the change in chemical potential plus number of moles of B into the chemical potential of B. Can you derive this yourself? Are you understanding? Aditya, are you understanding?
Yes, ma'am.
Okay. So if you can understand this, since G is a state function at constant temperature and pressure, we can say delta G equal to 0 at equilibrium. So what I can get is number of moles of A into the chemical change in chemical potential of A plus the number of moles of B into the chemical potential of B equal to 0.
Yeah, ma'am.
Okay, so that is what the Gibbs-dewham equation is. Initially, the fundamental equation of G was this: summed over chemical potential in the number of change of moles of in the species. But in Gibbs-dewham equation, you have the number of moles of a particular species into the number of the change in chemical potential of the ith species, summed over all the components in the system should be equal to 0. That means if I have a binary mixture at a given temperature and pressure, if this is going to be the thing, if 1 and 2 are the two components present, the moles of 1 into the chemical change in chemical potential of 1 plus the moles of 2 into the chemical potential of 2 should be equal to 0. Or otherwise, the change in chemical potential of 1 is equal to nothing but minus d2 by d1 n2 by n1 into change in chemical potential of 2.
Yes, ma'am.
Okay, so the chemical potential of one component in a mixture cannot change independently of the other. Same is true for the partial molar quantities, all other partial molar quantities. The system always tends to go to minimize the chemical potential. Okay, am I clear? So we have done the Gibbs-dewham equation. Gibbs-dewham equation is nothing but the summation of the number of moles of a species into the change in the chemical potential of that species in a system, which is summed over to give a value equal to 0, so that the system is always going towards the minimization of chemical potential. Chemical potential is also a potential term, energy term, so that should be also moving towards a direction where you have minimization of the chemical potential. The chemical potential is always going to be driven from a higher level to a lower level.